Okay.
Really? Okay. Okay. So, so today's plan is to first conclude what I planned to do yesterday, which was completely, not really unrealistic. So there is the end of the proof of Merlin's proof of the no crystallization theorem in V equal 2, plus description of the harmonic approximation. This already takes more or less half of the slides. Then I hope to have time to get to a discussion of dislocations and grains. And then maybe, I don't know, I will start introducing the model that I will discuss tomorrow in the 2 lectures tomorrow. Okay, so let me go back to the... so this is a dense slide because this is just a summary of the setting and definitions we already saw yesterday. So this is sort of reminder. I can go back if some definitions, you forget some definitions in the following slides. So I remind you the goal. So the goal is to exclude the particles interacting with a stable and temperate two-body potential in 2 dimensions can form a crystal associated, for instance, in the simplest situation, with a simple Bravais lattice with basis vectors A1, A2. So I want to show that it's impossible to form a crystal at any positive temperature in a suitable sense that I will remind in this and the following slide. It's not maybe the requirement of forming a crystal in this sense is a bit restrictive, but okay, this is a possible reasonable criterion. As I mentioned, there are other methods and other works that came later after Merlin's work that actually establish in a stronger form the possibility of having a breaking of translation invariance in such a setting. So here a reminder of some definitions. So we are in 2 dimensions. I enclose the system in a finite box with periodic boundary conditions. So the torus lambda L has sides parallel to A1, A2, and of length L times the length of A1, L times the length of the A2. So I want to arrange 1 particle per unit elementary cell. So the elementary cell is the parallelogram formed by A1, A2. And I want to discuss possible existence of a crystal in which each particle occupies 1 side of this lattice, or better, the restriction of this lattice to the torus lambda L. Okay, the interaction potential is a pair potential with pair potential small v. This index here indicates that since we enclosed everything in a torus, this is the periodization of the torus. In the shorthand notation, I will indicate V of Qi minus Qj just by Vij. The Qi's, Q1, Qn are just the coordinates in lambda L of the n particles. I have n equal L squared particles. And capital Qn is a big vector that includes the list of all the coordinates of the n particles. Then in order to try to prove existence of translation symmetry breaking, I need a pinning potential. So I consider this potential W, which is say a periodic function with degenerate minima at the locations of this of the sides of this lattice, and besides that is arbitrary. I indicate by this symbol the expectation with respect to the Gibbs distribution e to the minus beta phi. Here phi is the pair potential plus epsilon, the spinning potential. This epsilon, you should think of it as a small quantity that will be sent to 0 after the thermodynamic limit. Okay, other useful quantities. So this is the Bravais lattice. and it's useful to introduce also the reciprocal lattice. Given the two basis vectors of the direct Bravais lattice, you can consider reciprocal vectors that are the two vectors G1, G2, such that the mixed scalar product is equal to 2 pi delta ij. This is the Kronecker delta, and the reciprocal lattice is just the lattice generated by these two basis vectors. The first Brillouin zone is just the parallelogram associated to G1, G2. Is a bit like the elementary cell of the Bravais lattice. Now it's the elementary cell of the reciprocal lattice, it's also useful to introduce a finite L approximation of this first Brillouin zone, which is just the set of the allowed momenta within the first Brillouin zone. So these are integer multiples of G1 over L and G2 over L. These are the possible wave vectors associated with plane waves in the torus with periodic boundary conditions on the torus. Okay, and for any allowed momentum in the finite box, I also introduce this Fourier transform of the density, or if you like, density observable, essentially. This is, as you see, something that is in a suitable sense order 1. So it's the 1 over n sum over I from 1 to n of something that has absolute. So this is bounded by 1, if you like, uniformly in K. So Mermin's crystallization criterion is the following. So one should have that the thermodynamic limit of this Fourier transform of the density operator, which I denote by rho hat epsilon in the presence of the symmetry breaking term over the epsilon, computed at G, where G is a non-zero vector of the reciprocal lattice, is non-zero for at least one non-zero vector of the reciprocal lattice. Not only is non-zero, but also the limit as epsilon to 0 is different from 0. So somehow having a non-trivial modulation in the limit in which you remove the pinning potential after the thermodynamic limit corresponds to having a non-trivial value of the Fourier transform for a non-zero vector associated to the right modulation vectors. Okay, so the other property, so this is to say that there is a non-trivial component for Fourier vectors reciprocal to the Bravais lattice, and I would like to say that essentially for vectors that are not in the reciprocal lattice, the Fourier transform with the appropriate normalization goes to 0, and it goes to 0 in this average sense, in this weighted sense. And yesterday I justified why this is a reasonable request. So I take any bounded function from the Brillouin zone to R, and I would like to test either absolute value of rho k or absolute value square of rho k against this gamma, and then I take the Riemann sum restricted to all allowed k's different from 0. So I would like to show that this goes to 0 as L with P. Oh, oops. Something strange happened. Yes, there was a question.
The crystallization criteria is with respect to the definition of crystallization behavior of the temperature. So it's sufficient condition.
No, this is a bit stronger. It's a bit, it's a stronger requirement. So, there could be a weaker sense that is compatible with what I said yesterday. So in this sense, this is disputable. So one could say, okay, maybe Mermin's theorem tells you that you don't have crystallization in this sense, but it may be that one of the two. So I think that this is questionable somehow. That there could be a slightly weaker notion. If this is true in particular, what I said, Yeah, so it's sufficient. Okay. Okay. Anyway, I would like not to go back to the justification of this. There is some justification also in the notes I sent to Serena. You will download. So what I already anticipated yesterday. So these two conditions cannot simultaneously hold as a consequence of Bogoliub's inequality. So as I told yesterday, the proof of this is a simple consequence of Cauchy-Schwarz inequality with a suitable choice of the two functions to be chosen in the Cauchy-Schwarz inequality. In this inequality, psi I and phi I are just the function psi computed at qi and phi computed at qi. These two functions are two arbitrary smooth functions from the torus to the complex numbers. Okay, so now the point is to make a suitable choice of psi and phi to translate this into a useful inequality that will give us bounds on combinations of this sort. Again, I sort of sketch the proof. I think that there are all the elements for you to reconstruct the details. If you're patient, I mean, all the steps that that are not discussing are really elementary. You just plug in things and see what happens. But I won't do all the steps. Otherwise, again, I won't get to the point. But if you have any trouble in reproducing the computations, I mean, feel free to also recontact me back after these days. I mean, I will be happy to answer. So the idea is to choose psi equal to this exponential e to the minus I g plus k q. And phi sine of k times dot q. Here I'm choosing G should be the non-zero vector of the reciprocal lattice appearing in the Merlin's criterion, and K is a non-zero vector in the Brillouin zone. This should be a calligraphic. So if I just plug psi and phi in this way in the previous inequality, I get the following. So this is sum over I of psi I squared. In the right hand side, you get this combination. You get this phi. This is the sine of k dot q times the gradient of the exponential. So the gradient of the exponential brings downstairs a k plus g. So you get since there is absolute value squared, there is a k plus g squared. And then you get if you write the sine as e to the I kq minus e to the minus I kq, you get this thing. In the denominator, you have three terms as here. Choosing phi to be the sine, you get the three terms to be Laplacian v sine of kqi minus sine of kqj squared. And this you can bound for the purpose of the lower bound of this, that is an upper bound of the denominator. You can bound this difference just by k squared qi minus qj squared. This is elementary. The second term was just Laplacian wi times phi. Sorry, this should be qi. Sorry. This was sine of kqi squared, and then for a purpose of an upper bound, I just replaced the sine squared by 1. And the last term was sum over I of gradient sine squared. So the gradient picks up a k squared, and then you're left with the cosine squared. Again, this should be a qi. And for the purpose of an upper bound, you replace this by 1. So you get n times k squared. Okay. So you have two terms proportional to k squared and the term proportional to epsilon. Sorry, here there is another typo. Here there is an important epsilon C2 here. I will correct this maybe in next round. So C1 is just the coefficient of k squared. So it is, there is also this quarter that I bring downstairs. So this C1 is 4 times the coefficient of k squared. So it's 2 beta this plus 4. And I divide everything by n. So I divide numerator and denominator by n. C2 is just the coefficient of epsilon, so it is 4 times beta divided by n. Okay, so this is the after division by n is what you get. So this is the thing you would like to say that is different from 0, ideally. And this is the thing, when k is different from 0, this is the thing that should go to 0 after averaging on the basis of the second part of the criteria. So in order for both items of the criterion to be verified, this should be different from 0 uniformly in L and epsilon, and this should go to 0 in the thermodynamic limit, essentially. Okay, so what do I do? So I choose a smooth non-negative function supported in a sufficient, so a small bump. So gamma is a small bump of integral 1. And I multiply both sides by this gamma of k and I sum over k with the appropriate 1 over r squared. So this is a Riemann sum approximation of the corresponding integral. I have, so on the left side, I have what I get here after expanding the square. So I have a sum over ij, there is the term with j equal I that gives you n, which simplifies with the 1 over n. This is the 1. And then I have the terms with I different from j, and this is what you get. On the right side, I have exactly the same thing that I wrote before, multiplied by gamma and summed over the k is different from 0. Okay, now I let L to infinity, possibly along subsequences to guarantee that the limits exist. So as I said, if the part 2 of the criterion holds, then the contribution from this term go to 0. So somehow I wrote this part exactly in the form required for that term to go to 0. Okay, so the contribution from this goes to 0. This term now is independent of k, so it goes outside, and I get the following. So here alpha 0, alpha 1, alpha 2 are constants that bound, if you like, the possibly subsequential limits of the involved quantities. So let me temporarily assume that the limits of these 3 objects, so this thing here, this C1 and this C2, again, there is a missing epsilon, which is very important. I'm sorry for... so I'm assuming that these guys in the limit L to infinity either converge to something or at least they are uniformly bounded. This is a priori not obvious, but let me temporarily assume these 3 conditions. If this is the case, then I get in the limit I get this inequality. So on the left side I get just 1 plus alpha 0, the bound on this. The integral of gamma is equal to 1 with my normalizations. Then I get this constant, then a lower bound on this k plus g squared, which is something order 1. And then I have the integral over k of this. So this is like a small bump, like a Gaussian or something like this, but compactly supported. And then I have something like 1 over k squared plus epsilon with some constants. So we are in 2 dimensions. So so this is d2k over k squared plus epsilon. So this is for epsilon equal to 0. For epsilon equal to 0, this is log divergent. For epsilon positive, this is log epsilon, essentially. So you see, you have a constant independent of epsilon larger or equal than rho epsilon squared times log epsilon. This means that in order for this to hold for any epsilon, sending epsilon to 0, this means that this must go to 0 like an inverse log. So this shows that this limit is 0, even though it goes to 0 very slowly, like 1 over square root of log. So this is, if you like, the end of the proof, modulo the fact that these quantities are bounded. Okay, why this is not obvious, because these quantities, this one, and if you remember C1 and C2, they involve summing over particles of averages with respect to the Gibbs measure of something. So this is complicated. In general, if you take a generic pair potential, it's very difficult to evaluate this average. So why can we safely assume this? Okay, this is also, I think, if you never saw, this is a very nice observation. So this follows essentially by Fisher's theorem on existence of the thermodynamic limit. I don't know if you know it, but it's a very classical subject in statistical mechanics. So it's in any mathematical physics-oriented book in statistical mechanics, there is the proof of this very classical theorem. So the idea is the following. So define the partition function of a particle system in which, in addition to the potential we really have, we have some auxiliary potentials here. So there is two auxiliary contributions to the pair potential corresponding to the terms we want to average. An additional pair potential Laplacian Vij Qi minus Qj squared, and an additional term proportional to gamma Ij, this term here. And then an additional pinning potential, if you like, associated with Laplacian Wi. Okay, the idea is to introduce this lambda eta rho as auxiliary parameters you can use in the sense that by differentiating the log of z with respect to lambda eta rho, you generate these averages here. Okay, so the proof goes as follows. So you introduce this auxiliary potential, auxiliary because of the presence of these extra terms proportional to lambda eta rho. This is a stable and tempered potential, exactly as the original one we have. So the theorem of the existence of the thermodynamic limit for the normalized log of the partition function holds. Okay, you may not know this theorem, but the theorem states that if the potential is stable, stable means that you have a lower bound proportional to the particle number, as mentioned yesterday, uniformly in the location of the particle. Tempered means that the two-body potential decays at infinity in an integrable way. So if the potential is stable and tempered, then you take the log of the partition function, you divide by n, you take the limit n to infinity, and this converges. So the limit exists, is finite, and is convex in lambda eta rho, even in epsilon. Is convex in epsilon lambda eta rho. So this is a very fundamental theorem in statistical mechanics that, if you don't know, I recommend you study. So notice that this is what I was mentioning. If you take the derivative of the log with respect to the normalized log with respect to lambda or eta or rho, and you set after the derivative, you set the auxiliary parameters to 0, you reproduce exactly the averages that enter the definitions of C1, C2, and this combination here that appears. So the derivatives of the normalized log reproduce exactly the objects we want. So we want to say that in the thermodynamic limit, these guys are bounded uniformly in n. Okay, this is immediate from the fact that the limit is finite and defines a convex function. Because by convexity, the possibly subsequential limits of these quantities are bounded simply because the derivative of a convex function in an internal point can be bounded by the slope of any secant passing from that point. And so this means that the derivative can be bounded by twice the maximum of the function divided by the distance of the internal point to the boundary. So once you have a bound on f and you know convexity, the bound on f induces a bound on the derivative and therefore on those quantities. And this concludes Mermin's theorem. And I think it's a nice illustration. So the reason this is not crucial for this course, but I think it's a very nice proof that if any of you that allows one to introduce two important notions. One is the relevance of this theorem of existence of the thermodynamic limit and of the convexity that is included in the proof of the theorem of the partition function that you can compute in the presence of auxiliary fields that you can use to generate somehow extensive averages of extensive quantities normalized by the particle number. So this is a very general strategy to get uniform bounds in the thermodynamic limit of objects of this formula, which may be useful in many applications. And another thing is, I think it's very nice as an illustration of a so-called infrared bound, so a bound on non-trivial correlation functions in terms of essentially the inverse green function of the Laplacian, or a bound on the inverse green function of the Laplacian. No, sorry, of the green function of the Laplacian. Okay, so this concludes part of what I intended to say yesterday. And the next topic that I plan to discuss yesterday, that I should be able to discuss today, is the quadratic or harmonic approximation that I also mentioned. Okay, so as I mentioned, many of the things one knows or uses as basis for understanding what one should expect the system to understand how one should expect the system to behave. So one strategy is to introduce a simplified model that is treatable, and the first, typically in many situations, the first basic model, treatable, integrable model that one can introduce is based on performing a quadratic approximation around the minimum. So I go back to the potential energy we would like to understand the minimizers of, or possibly the low temperature states, Gibbs states of, and I imagine to be in a setting in which someone tells me that the minimizers consist of particle configurations arranged in a regular lattice. So, for instance, if you take the potential considered by Radin or Tile in 2 dimensions, in particular, if you take this sort of Lennard-Jones potential with a very deep and narrow well, I know that the minimizers of this function are portions, if you like, of the triangular lattice. And similarly, this is what one also expects to be the case with triangular lattice replaced by the face-centered cubic lattice in 3 dimensions. There is, as I mentioned yesterday, there is no proof of the fact that the FCC lattice configurations minimize a pair potential of this sort. There is a result by Flatley and Tile proving that this is correct if you add a specifically designed 3-body term, but everybody believes that the results should also be true for the potential of this. Okay, let me now describe how to go from this, heuristically at least, from this to a quadratic model. By the way, maybe the way I'm describing is not the shortest one, but it also hints at how one, in principle, in perspective, one might try to attack the problem, the real problem. I mean, how to attack the problem of showing that the real system behaves close to the harmonic approximation. So one starting point could be the following. So if you take any particle configurations, for instance, in 2 dimensions, it's simpler to define certain objects and to draw pictures, but similar things can be also discussed in 3 dimensions. So if you have a particle configuration in 2 dimensions, you can always uniquely associate to the particle configuration a so-called Voronoi tessellation. So this is partition of the plane induced by these particles as a union of these cells that are whose boundaries are drawn in the picture with these solid lines. So these regions here are the regions of points in the plane that are closest to this point as far as this region is concerned. This region is the set of points of the plane that are closest to this point, and so on. So the Voronoi cells are the regions of plane that are closest to a given particle in this particle configuration. So the boundaries of these cells define a graph, and the dual graph to that graph is a triangulation, and is the graph. So I mean that all faces are triangles. In general, the number of the incidence number of each vertex of this graph is not constant, is not always equal to 6. You see this incidence number is 6 here. Here it's 6. Here it's not 6 also. This is 5 instead. So the incidence numbers in general is not constant. But all the faces are triangles. So this is very general. You take any configuration, you can always draw this diagram. Okay, a reasonable approximation. So in a suitable sense, the pairs connected by this dotted line are in some sense nearest neighbors. Or you can, I will call them nearest neighbors. And if the potential phi is consists of a very deep and narrow potential well, it's likely that low energy configurations corresponds to bonds, nearest neighbor bonds, that are all of length approximately equal to the equilibrium length. Because otherwise, I mean, you get very large energy from the fact that you're putting the two pairs of particles at the wrong distance. Once again, imagine that the potential is like this, with this very deep minimum at distance 1. So, of course, any pair of particles likes to be at a distance, an equilibrium distance 1, and you pay a lot if they're not at distance 1. So it's a reasonable approximation to say that that all the bonds have length that is very close to 1. Okay, so this is again a hint to what one could try to do in real life. So one could try to look at the generic configuration in terms of this Delaunay triangulation. This is the name of this, and try to get a priori bounds on the energy that tells you that typically the lengths of this modulo some rare defects are all of length approximately equal to 1. Okay, so if they're all approximately equal to 1, okay. So we know that the minimizers consist of regular triangular lattice. Okay, here it comes a more serious approximation that looks reasonable, but it's not so reasonable. So let's say that the Delaunay triangulation is isomorphic to the standard triangular lattice. This looks reasonable, but it's not so reasonable because this excludes, for instance, the presence of defects of this sort in which the incidence number is different. So these are precisely these dislocation defects that I mentioned, or are related to the dislocation defects that I mentioned, and typically at low energies there are rare dislocations here and there. So in real crystals you will see at low temperatures dislocations. Maybe there are not so many dislocations, but there are some. So this assumption excludes the presence of dislocation at all, which is not a reasonable assumption, but let's do it for the purpose instead of for the moment, for the purpose of gain some intuition about the problem. So you know, if yes,
to assign particle to the reference.
Yes. Yeah, no, but okay. This is not. We will see probably tomorrow, because I'm going as usually slower than expected, that in the Risa-Ortiz model, there's a way to associate particles to a reference regular triangular lattice, but still have this location. So somehow here the point is that you're assigning not only particles, but also to pair of particles. You're associating particles to reference vertices and nearest neighbor particles, those connected by these bonds, to bonds of the. So this is too much. So there is a way to somehow label particles so that they are associated to a triangular lattice, but then allow bonds to rearrange a little bit. So you may say that the bond of that pair of particles is not the one, the naive one, but is the naive one plus an additional vector that describes some sliding. And this sliding is exactly the effect of these locations.
So you assign both I and J.
Essentially, yes. Okay, so this is what is not good of the approximation, but again, I'm discussing this because somehow it's the basis to a better approximation that will come. Okay, so if I have if the graph, if the Delaunay triangulation as a graph, including vertices and edges, is isomorphic to the regular triangular lattice, and as I said, I expect that the location of particle is close to the ideal location of the regular triangular lattice, I can write the position of each. So first of all, I can label positions of the particles with the sides of the ideal triangular lattice, and I can write the position of that as xi plus plus a displacement vector that typically should be very small. Okay, and the harmonic approximation or quadratic approximation is just a second order expansion of this energy here in U. Sorry, I forgot to discuss this formula here. So what I said is, so this is an approximation to go from here to here that is presumably not so bad. So this I tend to believe that there is nothing serious going from here to here. So as I said, the Delaunay triangulation is always well defined, and if you have a function that is very potential that is very deep and narrow, presumably you can actually drop in the energy all the terms that involve next to nearest neighbors and beyond. So you retain only the interaction among the particles connected by bonds. So you in this way you re-express the original energy in an approximate form in terms of a graph of an energy per potential energy defined on a graph. Notice, however, that the graph depends on the particle configuration itself. So it's not an approximation in terms of a fixed lattice. So the approximation in terms of the fixed lattice comes in the next slide. So I think that going from here to here should be reasonable. Or I mean, if you are able to say something about this model, I think everybody would be very happy.
In the Radin example, this would be almost exact, no?
Exactly. Yeah, in fact. In tile, so all point essentially of tile proof is that he allows for these polynomial tails. So he really has to discuss the remainder term that you get by neglecting, say, this next to nearest neighbor term. So this is essentially the additional difficulty. So he has a rigidity estimate allowing to bound sort of a priori in a convenient way those terms. Okay, so this is again now, as I mentioned, an additional quite serious approximation. Here, once again, the bad part of the approximation is not the fact that I'm replacing that I'm replacing this the potential by the quadratic approximation. That's not the most serious thing. The problem is that I'm replacing the graph isomorphically by a regular triangle. This is the more serious part of the approximation. So, for instance, many of the things that I will say about this quadratic model can also be extended to a non-quadratic model with the fixed. So, if you have a fixed triangular lattice and you allow for this plus small quartic term, you can also say things. I mean, it's not trivial, but there are results in that. Yeah, for instance, Eris knows about those kind of results. So yeah, this the problem of understanding Gibbs measure associated to a potential like this, but with an additional quartic, say, terms with the gradient structure is a subject of many papers in analysis and mathematical physics, and can be done either via renormalization group methods or via softer methods like Helfer-Sjöstrand inequalities or Braskamp-Lip inequalities. So, but okay, if you have a quadratic, so even if you have quadratic plus quartic, you can say many things, but if it's just quadratic, you can really make computations. Okay, so this is the harmonic approximation in 2 dimensions associated with triangular lattice. You can of course do a similar analysis in 3 dimensions using another reference lattice, for instance, the FCC lattice. For later reference, let me observe that the FCC lattice is also a simple Bravais lattice, and these are the basis vectors of the FCC lattice. Okay, this is something that, for instance, I didn't know before, and it's because the FCC lattice, if you look at it, often is drawn in a way that it doesn't look like a simple Bravais lattice, because the FCC lattice is like a cubic lattice in which you draw additional, in which you insert additional particles at the center of the faces. So if you do it like this, it seems like that the elementary cell is this one, and there are many particles in the elementary cell. But there is a way of defining the elementary cell in a better way, showing that this is actually a simple Bravais lattice, and these are the basis vectors of that Bravais lattice. Okay, so the harmonic model is by definition the statistical mechanics model with Gibbs distribution e to the minus beta H harmonic, with H harmonic is is this one. So you can say that this is a model defined independently. Of course, the reason why we believe it's relevant for this problem is that at least heuristically, this is the way it's connected with the original problem. Okay, now notice that this Gibbs measure is Gaussian, so we can compute everything. And in particular, we can ask ourselves whether the model exhibits positional long-range order or orientational long-range order. So let me define what I mean by positional long-range order, and orientational long-range order has a similar definition. So we can set things up in a way similar to the way in which I set things up in the definition of positive temperature crystallization yesterday. So I take a finite L, I let L sub L, the discrete torus obtained by taking a portion of the ideal lattice, either the triangular one or the FCC, of sides LA1, LAD with periodic boundary condition. We define the finite volume Gibbs measure with the symmetry breaking term epsilon as the measure with this probability distribution. Here there is an additional pinning potential, which I also choose quartic. This was probably a question related to what Dimitri. So here I can decide to choose a quadratic pinning potential, and if I want to have a fully solvable model, that's the best choice I can do. And okay, so here everything is quadratic. we say that the system exhibits positional long-range order, that I will write LRO for long-range order. If these two things happen, so I take the average quadratic displacement of arbitrary particle. Since I have periodic boundary conditions, I can choose the one close to 0. I take first the thermodynamic limit, then the symmetry breaking parameter to 0. I would like this to be typically positive, but small as beta. So remember that U is the displacement with respect to the ideal position. So if the displacement is 0, this means that the particles are exactly in the ideal position. If the quadratic average displacement is small for beta large, this means that at small temperature, typically I'm very close to that position. So this is one instance, and then another instance is that the particles at faraway distance are correlated in this sense. And actually, the C2 should actually be whatever, either equal to C1 or maybe there is a factor 2 or something like that. Okay, but in order not to think about factors 2, I just wrote two different functions. I would like to say that if these limits are positive, but they tend to 0 as beta to infinity, I would say that the system exhibits positional long-range order. Okay, so of course, in a Gaussian model, I can compute all these averages, and this is very easy. So in order to compute the averages, I just have to understand the covariance associated to the quadratic form. To understand the structure of the quadratic form here. And this will just be the covariance computed at 0, and this will be related to the covariance computed at x1. So I'll focus on the proof of the first part. The proof of the second equality is exactly the same. So there are questions? No. Okay, so as usual, so here I have, not by chance, I chose periodic boundary conditions in order to be able to write eigenfunctions and eigenvalues of the quadratic form particularly easily. So as usual, eigenfunctions of the quadratic form in this torus are just plane waves with the allowed case, as sort of mentioned already before. I will use a convention of Fourier transform of this form, so that this summation normalized by 1 over L to the D converges to the appropriate integral as L to infinity. Using this convention, the diagonal form of the spinning potential is already in diagonal form. So this is written, if you like, in real space by Plancher's identity. You can write the same in K space. The non-trivial part is the H harmonic. You can just check it if you just represent UX in this way. You can rewrite it in this form, and you have where it's written. Yeah. So somehow what I'm getting, I'm writing this as U hat K e to the I kx. This is e to the I U hat K e to the I ky, and x minus y is the nearest neighbor vector of the triangular lattice. So this is what I'm calling AI. So these AIs are the nearest neighbor vectors either of the triangular or of the FCC lattice. So there are in the summation, so in the triangular lattice, I have 6 neighbors. But if I want to perform summation without overcounting, I can sum for each side over 3 neighbors. And if I do so, I will count over all nearest neighbor pairs. For the FCC lattice, I have 12 neighbors, and if I want to sum over all nearest neighbor pairs, in order to avoid overcounting, I can sum over all sites plus 6 neighbors. Okay, so the summation over I and these AIs is just a summation over these 3 or 6 nearest neighbor vectors in the 2 cases in which I have the triangular or FCC lattice. And this 2 times 1 minus cosine, so yeah, this this U hat dot AI is what comes out of the U hat times this difference here, which is just the nearest neighbor vector. And then the 1 minus e to the minus ik x minus y is what gives rise after summation to this 1 minus cosine. Okay, this is a very elementary computation that I invite you to do if you have the patience. Of course, I can write this more explicitly as a quadratic form with inverse covariance matrix A hat of k. So A hat of k is just summation over these nearest neighbor vectors of 1 minus cosine times the projection in the direction AI. In d equal to, we can choose the 3 vectors to be the following. So let me maybe make a picture. So this is a portion of triangular lattice. I'm denoting A1, this vector here. Maybe use color chalk. This is A1. This is A2. It's not very colored. And this is A3. So what I was trying to say before is that if you want to sum over all nearest neighbor pairs, you can sum over each vertex, and per vertex you just sum over these 3 vectors. If you do so, when you sum over all vertices, you get all nearest neighbor bonds. Because, for instance, it seems like you're missing these 3 guys, but this guy is the A3 vector exiting from here. This guy is the A1 vector exiting from here, and this is the A2 vector exiting from here. So that's why it's enough to sum over 3 nearest neighbor vectors per site. Okay, and there is a similar choice for the FCC lattice. Okay, so you can actually really, so if you want to understand what's the behavior of A hat of k at low k, you can do the following. So you expand the cosine, so you write A hat as the term that is k squared plus a term that is k to the 4th. The term that is proportional to k squared is just this one, and it's easy to check that the eigenvalues are all of order k squared as k to 0. So this is again a computation, an exercise. If you never did it, I invite you to do it. You just write down things. So if you for these 3 nearest neighbor vectors, you write sum over I from 1 to 3 of this projection squared times the projection matrix in direction A1, A2, A3, you get this matrix here. This is just 3/8 k squared times the identity plus this 3/4 k tensor k, and the eigenvalues are therefore 3/8 and 9/8. So from this computation, what do we get? So we get that the average square displacement at 0 is just if you pass to here there is a U hat missing, is just the sum over k properly normalized of the average of U hat k squared, and this average now can be computed, using the fact now the Gibbs measure is diagonal, is block diagonal, if you like, in K space. So this is just the inverse of A hat of K plus epsilon, the identity. The epsilon identity comes from this contribution here. and the A hat comes from that. Okay, so this is just, so this identity just comes from the computation of a Gaussian integral. Now, in the thermodynamic limit, this 1 over L to the D summation over K, which is a Riemann sum, just tends to the corresponding integral. We said that this A hat of K behaves for small k like K squared. So this is like the integral in decay of 1 over K squared plus epsilon, just to dimensionally have a feeling of what you get. So in 3 dimension, 1 over K squared plus epsilon is uniformly integrable as epsilon to 0, and I get just something that is order 1. Notice that there is a 1 over beta in front, coming from the fact that there was a beta here. So so there is 1 over beta, 1 over A hat of K plus epsilon. So here I forgot the 1 over beta, which is crucial. Sorry again for the typo. So I get 1 over beta times something finite in 3 dimensions, while in 2 dimensions I get 1 over beta times log. So this means that the average displacement diverges to infinity in 2 dimensions. This means that you don't manage to pin down particles. If you put a small pinning potential, as long as the potential is there, particles tend to be relatively close, but not so much. They can have log fluctuations. But if you after the thermodynamic limit you send the intensity of the pinning potential to 0, they just randomly move in the plane. So there is no positional order in 2 dimensions, which is in line with with Mermin's proof via Bogolyubov's inequality. It now becomes, I think, clearer why I was referring to that bound as an infrared bound. So infrared means small k. Somehow the Bogolyubov's inequality gives you a lower bound on a certain quantity in terms of an integral that dimensionally behaves exactly in the same way. It's the integral of 1 over K squared plus epsilon. So the key of Bogolyubov's inequality is that it gives you a lower bound on an appropriate quantity in terms of the same kind of quantity you get in the harmonic approximation. So this is a significant fact of the Bogolyubov's inequality. Okay, so the harmonic model predicts positional long-range order in 3 dimensions and no positional long-range order in 2 dimensions. So in this sense, Mermin no crystallization theorem is a rigorous confirmation in the real model of this prediction based on this other model that you can maybe think as an approximation to the original model, or maybe not. Okay, you can now look at orientational long-range order. Of course, in 3 dimensions, if you have positional long-range order, you also have orientational long-range order. What do I mean by orientational long-range order? So in 3 dimensions, particles, I'm saying the particles are typically close to the ideal location of the crystal. So I really see, essentially, if I make a picture of a typical configuration, I see really particles close to the triangular lattice. In 2 dimensions, the harmonic approximation predicts that particles are not pinned at any specific position. They tend to fluctuate a lot, like this log as epsilon to 0. So if you try to follow the particle that I labeled with site 0, it will be far away typically. But what could happen? So there is no positional order in this sense. It's not pinned close to 0. But what could happen is that if I look at the pair of particles that are nearest neighbor in the sense of the Delaunay triangulation, it could be that they are both typically very far away from the origin, but they could be very far away with a local structure that is similar to the triangular lattice. So it could be that the triangular lattice itself can compress globally quite a lot. But if you make a picture, you will see typically particles that are still arranged in a triangular lattice. So this would correspond to breaking of rotational invariance. So the particles themselves can fluctuate, but if I look at pairs of nearest neighbor particles, they are typically oriented like A1, A2, or A3. This would be very nice. And in fact, the same compute. So this means that rather than looking just at U at the point, I should look at the vector associated with the difference of two neighboring vectors. If this quantity here is small, I may say that I have orientational long-range order. In fact, exactly the same computation I just showed tells that in the harmonic approximation, in the harmonic model, this quantity here is equal to the integral of the same 1 over k squared plus epsilon times 1 minus cosine of k a1. Now, this integral here is uniformly, again, I'm missing a 1 over beta. I'm sorry, there is a 1 over beta here, 1 over beta here. I will correct this before, maybe, okay. I will correct this. So now this integral is uniformly bounded as epsilon to 0, both in 2 and 3 dimensions. There is an extra 1 over beta that I didn't write here in front. So this means that the relative displacement of two neighboring particles, so even if these two particles are very far away from the origin, they're close to each other, and actually one can also show that they're in the right direction, either this one or in one of the 6 directions of the triangular lattice, in this sense. So this is why the harmonic model suggests that crystals in 2 dimensions, even if they don't exist in the sense that they don't pin, they may look locally as triangular lattice. Okay, this is one reason why one should maybe think that rotational order is there in 2 dimensions. As I already started to mention, a big limitation of the harmonic model is that it doesn't account for dislocation defects. So for instance, defects in which one particle has 5 or 7 nearest neighbor in 2 dimensions rather than 6. So as I already mentioned, the predictions of the harmonic approximation can be generalized to non-harmonic models. So there are a number of results for gradient anharmonics Gibbs measures due to, say, for instance, Bridges and Yau, and now since I didn't write down the list, so that there are results by Adams, Mueller, and Kotetsky. Many result in that. So there are results by Spencer and collaborators for models that look, as I mentioned, models that look like this with an additional quartic, say, a small quartic gradient term. There are also results in which there are additional defects, not only quartic term, but you may even have lattice defects in the form of missing atoms. So rather than having dislocation, you sort of randomly take out a point, but the overall triangular structure remains. So if these lattice defects are rare enough, also you can prove existence of positional order in 3 dimensions and orientational order in 2 dimensions. So this is not the real point. I'm not saying that these results are easy. I mean, there is serious mathematical work to prove this kind of things, but somehow there are no real obstructions, and there are a number of quite significant results. The problem of all these models is that they don't account for dislocations, and dislocations are the real source of problems, and I mean, not only problems, but of interesting phenomena. I mean, they really are the key to explain real behavior of crystals in 2 and 3 dimensions. Okay, so here is a picture of 2 kind of different dislocations. So a dislocation defect is a defect of the crystal that cannot be seen locally as a smooth deformation of the reference lattice you would like to prove existence of. Here, to make things simple, I I reported two pictures, not of the FCC lattice, but rather of the simple cubic lattice that is a little simpler to draw. So this kind of defect is called an edge dislocation. It's a bit like inserting half plane of an extra, so an extra half sheet of lattice at a certain point. You see, you should think of this as a half plane inserted at a certain point. And here instead is another kind of dislocation called screw dislocation. Here is something you produce a sort of fracture in which at a certain point you sort of slide one plane with respect to the next one. So these are two different kind of dislocation. Maybe there are others, but I'm not an expert in this. I mean, there are in solid state books or there are books dedicated to the theory of dislocation, to describing particular phenomena like plasticity in solids. So if you want to understand the plasticity or understand elasticity, I mean, you have to enter into this kind of discussion. One relevant feature is that if you look locally, so here you see, in order to produce this defect, I inserted this infinite half plane somehow in the middle of the lattice. But somehow you notice that something is wrong. If you look locally, you notice something wrong only if you are close to here or to the analogous sites inside the picture. So in this section, the only point in which you see locally something strange is here. Here you see there are 5 neighbors rather than 4 neighbors. All the other guys have 4 neighbors in this section. There is also a way, but actually there is a way to find out. So essentially, up to this sort of zero measure set of, I mean, this one-dimensional set of vertices, most of the vertices have locally the good structure around. There is a way actually to realize that there is a problem moving in circuits passing only through non-problematic sites. And this is the way to define what is called the Burger vector B. So imagine you start from yes, in the picture to start from this point. You move, I don't know, here, 2 steps to the right, 3 steps to the, no, sorry. You move 3 steps to the right, 3 steps down, 3 steps to the left, 3 steps up. In a situation in which you have no dislocation, no defects, you should come back to the same site. If you are not coming back to the same site, then there is something wrong that is encircled by the path. So somehow this is a way to find out that there is this line defect passing through the edge of the half plane. Just moving in circuits involving only the good sides. So there are, when you have this circular path, so if you try to move in this circular paths, and the circular paths encircles the defect, then you will see this displacement, and the displacement is called the Burger vector. In this case, the Burger vector is this horizontal vector on the left that connects the initial point of the path to the last point of this unclosed path. And similarly here. So if you start from here and you go 1 step to the right, 3 steps down, 3 steps left, 3 steps up, and then 2 to the right, again you don't close the circuit. So there is a sort of wrong vector, defect vector B, that now is orthogonal to the plane, to the portion of plane encircled by delimited by your circuit. So depending on whether this Berger vector is in the same plane of the circuit or orthogonal, you call these dislocations edge or screw dislocations. There is a classification of this. Okay. One computation you can do, and this is done in essentially all books on plasticity and these kind of things. You can look at pairs of dislocations far away from each other, and you can compute the effective energy associated to these pairs of dislocation. So it turns out that the effective interaction among dislocation behaves dimensionally like Coulomb interaction. So it scales like log at large distances in 2 dimensions, and like 1 over distance in 3 dimensions. So the dislocation interaction is a bit like a tensorial Coulomb interaction. Somehow the role of the charge is played by these Berger vectors. So it turns out that pairs of dislocation associated to pairs of Berger vectors Bi and Bj have this effective interaction in 2 dimensions, and then there is a similar formula in 3 dimensions. Once again, I'm not an expert of this, but these are classical formulas you find in books on elasticity or plasticity, and it's a classical computation. This construction, as if you know anything about this, is reminiscent of the discussion about vortex defects in the XY model. So in the XY model, so the XY model is a model in which at each side of a perfect lattice you attach a unit vector that you think of as a spin, and you have nearest neighbor interactions among spins proportional to the scalar product among these unit vectors. Ground state, if the interaction is attractive, so if the interaction favors alignment, the ground states just consist of all vectors parallel to each other, and at low temperature you expect that a typical low energy configuration consists of vectors that have small fluctuations around a fixed direction. However, here and there are some kind of more serious defects in which you have winding, non-trivial winding around the site, around the face, for instance, and this and you may actually label these defects associated to non-trivial winding to the winding number. So the winding number can be 0 if there is no such defect, or it can be proportional to 2 pi times it can be equal to 2 pi times an integer. This integer, so also in the XY model, same thing. If you have 2 such defects far away, they interact with the Coulombic interaction that again has a form somewhat similar to this in 2 dimensions and somewhat similar to 1 over r in 3 dimensions. So there are all these sort of hidden effective Coulomb-like charges that are associated to low energy excitations of these models with continuous symmetry. The effective Coulombic charges of the rotator model are just scalar charges, while the effective charges of these dislocation defects are vectorial, as I mentioned, and are labeled by these Berger's vectors. So in addition to this interaction energy, you also pay there is a local cost to have the wrong number of neighbors at the location, at the so-called dislocation core. So at the dislocation core, there is a sort of local energy coming from the fact that you have the wrong number of neighbors. And then there is a long-range interaction coming from the pair interaction of these locations or vortices far away from each other. So driven by this, so motivated by this observation, Kosterlitz and Thouless in 1973, in their famous paper about the rotator model, they also studied in this perspective two-dimensional crystals. So they proposed to describe these two-dimensional crystals in terms of an effective model of interacting dislocation cores. So every dislocation core came with a local energy cost associated with, ideally with the wrong number of nearest neighbors, plus a Coulombic logarithmic long-range interaction. So, and this is the paper where Kosterlitz and Thouless introduced this notion of vortices, and they proposed a heuristic low energy treatment of the behavior of the system, looking at the system as this collection of charges. So this effective model introduced by Kosterlitz and Thouless and then further investigated by Nelson and Halperin and Young in 1979. So this is a model of melting of two-dimensional crystals, if you like, known sometimes in the literature as the KTHNY model for Kosterlitz, Thouless, Halperin, Nelson, Young. The predictions are the following in two dimensions. So there are two critical temperatures. So one critical temperature below which you have algebraic decay of positional correlation and orientational long-range order. There is a second range of temperatures in which you have exponential decay of positional correlations and algebraic decay of orientational correlations. And then above the third range of temperatures, high temperature regime, in which you have exponential decay of all correlation. So this, once again, predicts in particular that in the very low temperature regime, you have orientational long-range order. So this is a more serious model, taking into account, it's still an effective model like the harmonic model, but this accounts for these locations. And also suggests existence of orientational long-range order. So this is a more serious indication that orientational long-range order should be there. Okay, but still there is a but, because it's not clear. So this model somehow implicitly assumes that these locations are sort of rare. In two dimensions, you have this rare gas of dislocation. So it's not clear that this is the correct picture, because typically, at least on the basis of numerical simulation or of real experiments, typical crystals tend to form grains with constant orientation. So rather than having rare dislocation here and there, typically dislocations are arranged in closed path in two dimension or in closed surfaces in three dimensions. So this is okay. Of course, this is a picture of a section of three-dimensional crystals, but nowadays people can do amazing things, do almost two-dimensional crystals, even experimentally. These are the typical picture you see. So the system tends to form islands called grains. Within each grain, you have essentially an essentially perfect portion of crystals, say triangular lattice or FCC. And in different neighboring grains, you have different orientations. So you have like a bunch of perfect or essentially perfect triangular lattice, maybe with small, very small defects, maybe a little bit compressed or deformed, but essentially a perfect lattice. And then in the next grain, you have a perfect lattice, but rotated by a finite angle, and so on. So these are the typical configuration you observe in simulations and experiments. So if you look microscopically, so unfortunately this picture is with a square lattice, but you may do similar pictures if you were able. I'm not very good at taking pictures at the computer, but so I took from a paper. This is typically what happens close to the grain boundary. So this is sort of zoom of two neighboring grains. So you have a perfect crystal here, you have a perfect crystal here. They are rotated with respect to each other. Along this line, there are mismatches. So there are certain vertices that have the right number of neighbors, and here and there are certain defects like those associated with dislocation. So this is a dislocation. Again, here you see there is a missing bond. Here also there is. So there are every one and then there is a dislocation along this line. So you can actually think. So if the offset angle is very small, you will have actually rare dislocations all along that line. If the offset angle is big, then you will have plenty of dislocation along that line. In any case, you will have a finite density of dislocation along that line, or if you are in 3 dimensions, there is a finite line density along this line, or in 3 dimensions there is a finite surface density along the grain boundary that is 2 dimensions, 3 dimensions.
The dislocation is on the grain boundary?
Yes.
It starts and then it goes.
Yeah. This is so in 2 dimensions, dislocation are just points. In 3 dimensions, they are lines. So
there will be a plane.
No, there will be, for each of these guys, there will be a line in the orthogonal direction.
And the grain boundary.
And then there will be.
And the grain boundary will be 2-dimensional.
Yeah, so there will be this in this 2-dimensional plane. There will be lines of dislocations, essentially.
So dislocations are the support of the grain boundary.
Exactly.
And only there.
Yeah. So in a situation like this, you see dislocations are typically close to each other. So once again, this effective model proposed by Kosterlitz-Towles uses this pair interaction, but this is the pair interaction obtained by looking at the asymptotics of 2 isolated dislocations. So it's not clear that this model accounts for the formation of structures in which you have density of these objects close to each other. Okay. There is an amazing thing, which I mean, I never studied elasticity or plasticity theory while I studied electrostatics or electromagnetism, and I was very surprised to discover this fact. So now, grain boundaries, as I said, it should be thought of as say in 3 dimensions as a plane or surface supporting finite density of dislocations. These dislocations typically have constant charge. So on a given, so imagine you have 2 essentially parallel grain boundaries. Here you will have the charges will correspond to a Berger vector this way, and you have opposite Berger vector on the other. It's a bit like having a capacitor in electrostatics with so positive charges here and negative charges here. Now, in electrostatics, if you have a capacitor, the electrostatic energy scales like the volume enclosed by the capacitor. Okay, here it's amazing because for many respects things seem like behaving like Coulomb charges, but here if you have this sort of vectorial capacitor, the energy of the capacitor scales like the boundary, not like the volume enclosed by the capacitor. So so this is what I mean by grains have a finite surface tension. So grains are a bit like in this Coulomb analogy, a bit like capacitors because they have on the boundary these charges. You would then say, driven by this analogy with Coulomb system, you would say, okay, then the excitation energy scales like the volume of the grain. No, it scales like the boundary. This is because somehow, roughly speaking, the tensorial, so there is a tensorial structure. So there is this scalar products of vectors with the Burger's vector. So this creates some averaging, and somehow this averaging essentially changes a volume law into an area law. It's very, yeah, I don't know, I found it very surprising. So this is something that people in elasticity and plasticity know very well. So they know that the energy of grains scales like the boundary. So you have a surface tension. The surface tension, quite naturally, depends on the offset angle. So if you have a grain corresponding to two grains that have different orientation delta theta, the surface tension will depend on the value of delta theta. This is very natural. There is this asymptotic law when delta theta is very small. So when delta theta is very small, the surface tension scales like delta theta log delta theta. So this is a sort of this. So somehow, okay. So there is this strange log delta theta behavior. This corresponds to this cusp. So this is a plot. This is experimental. This well, I don't know. It's an extrapolation, I think, from simulations of the value of the surface tension as you vary theta. So this asymptotic behavior tells you the behavior here, this cusp here. And then when you have larger values of theta, you get this behavior. And you get these tips. These are sort of magic angles. It turns out that these angles corresponding to these cusps are the angles that are typically seen. So if you take a picture of a crystal, you see grains, but typically you don't see the neighboring grains at random delta thetas. You see that the relative delta thetas correspond to the values of these cusps here. So this is a quite complicated picture. I mean, the function here is complicated to derive microscopically. Already proving this delta theta log delta theta behavior is not trivial, but there are examples of microscopic models in which you can prove this. Okay, so now I think 5 minutes more and I get to the end of the section. Okay, now let me discuss in the perspective of a mesoscopic model of grains an argument that seems to point towards not having orientational order. So far I proposed the harmonic model that suggests the existence of orientational order in two dimensions. Then I proposed the improvement by Kosterlitz and Towles that also in the presence of dislocations here and there suggests presence of orientational order. So now let me propose another effective model. So now let me imagine that now the system is described at the mesoscopic level, in which we have these mesoscopic grains consisting of pieces of crystals with perfect ordering. And now I draw, so in the picture, an arrow indicating the direction of the crystal. Okay, so in this looking at this effective model of, so this effective model of grains now looks a little bit like a rotator model. It's a rotator model, however, in which the pair interaction of two neighboring grains with a small offset does not scale like delta theta squared, like in the standard rotator model, but rather like delta theta log delta theta. So in the standard rotator model, where the interaction is the cosine of delta theta, once you the interaction energy is like 1 minus cosine delta theta, so it scales like delta theta squared. In this case, in this model, the energy when you have a small offset, it goes like delta theta log delta theta. Okay, it's peculiar the fact that so in particular this interaction is not twice differentiable at zero. And the original proofs of Mermin-Wagner, of Fröhlich-Pfister, I mean, until quite recently, all the proofs of absence of orientational order for rotator-like models in two dimension required C2 interaction. In particular, they required that the interaction energy of neighboring spins or grains scaled like delta theta squared, small delta theta. Okay, so one could say, okay, maybe then for such singular interaction, you can have orientational order. But this is not the case. So in quite relatively recently, in 2005, Joffe, Schlossman, and Werenich showed that the Mermin-Wagner theorem also for singular rotator-like models with interaction scaling like delta theta equal to, I'm going to see. So if you use to describe the system of grains an effective model that is like a rotator model with interaction given by that kind of behavior, then validity of Mermin-Wagner theorem seems to suggest that you have no orientational order. So this seems a heuristic argument pointing towards the opposite prediction. Okay, I tried to talk with some people in plasticity and elasticity theory, and the reaction was that in real life you never see arbitrarily small delta thetas. So as I told you, if you take typical configurations, you only see neighboring delta thetas pinned at this sort of magic angles corresponding to these cusps in this plot here. So they told me, okay, I think that if you want to use an effective model of grains in this sense, you should only allow neighboring delta thetas belonging to the discrete sets of these cusps. So this would look more like a clock model, a discrete clock model rather than a rotator model. Okay, so if you look at this as a clock model, then you should have a low temperature phase with orientational order. Yes. Okay. In any case, so this kind of argument tells us that it's not really obvious. I mean, depending on how you put things, people may react differently about whether there should be in a realistic model orientational order or not in two dimensions. So motivated by all this, some years ago I started to study with Florian Theil a positive temperature version of a model originally proposed by Ariza and Ortiz as a sort of improvement of the harmonic model I proposed before, in the presence of these slips that allow for these locations. So at this point, I will introduce this model tomorrow. It's too late now. This model, from a kinematical point of view, not only it allows the presence of dislocation defects, but it also allows for grain and grain boundaries. And you can compute at the kinematical level somehow the energy of a pair of isolated dislocation and the energy of, say, of a capacitor, or if you like, of a grain. And in this model, you get both this kind of behavior at large distances for isolated defects, and you get that for grain boundaries, the energy gives a finite surface tension, and for small delta theta, you get exactly the Ritz-Shockley law. So it's a model that has a lot of nice features that seem to match with what you expect in real systems, and is, I think, simple enough to allow for analytical results. So my interest was to understand in this model existence or absence of rotational order in two dimensions. We failed for the moment. What we were able to prove is that in the three-dimensional version of the model defined in terms of a reference FCC lattice, the model exhibits both positional and orientational order. This is nice. And this is the main result I will state and give a sketch of the proof of tomorrow. I sort of believe that non-trivial extension of the methods we use in 3 dimensions should say something in 2 dimensions, but so far my attempts failed. But this doesn't mean that it cannot be done. And actually, if anybody is interested, I mean, I would be very happy to keep thinking about this problem. I mean, I proposed this to a postdoc, and we struggled on this problem for a while. Then, after 1 year, I decided to move to a simpler problem. But I don't think it's impossible. Anyway, so this motivates the model I will introduce tomorrow, which is this Arisa-Ortiz model that was the last part of today's lecture. But at this point, I will move. At least I will have the first part of tomorrow's lecture prepared. Good thing. Okay, thank you.